basics. So what I've talked about seismic data, seismic data acquisition and the basics of seismic method. That is going to be the base for seismic data processing, and to understand how the data looks like and how the data are processed to get a meaningful stack section or image of the subsurface from which we can delineate several structures like fault and anticline synclines, salt domes, and any kind of oil reservoir, mineral reservoir, or mineral assemblage, in fact. So seismic method, seismic data processing help in all those things. So today we'll be learning about how we can, we have learned in past, we have learned how to acquire the data, and today we'll learn how to process the data. So this work which I am going to, so first I'll talk about the basics and concept of seismic data processing, and then I'll discuss about a case study from on a real data from KG basin, that is Krishna Godavari basin of India, for the exploration of gas hydrates. Mind you, gas hydrates, not oil exploration but gas hydrates. Okay, so today's session will be very interesting, so please tune in, and if you have any question, feel free to ask in between, and we can have a discussion, and we can move forward with the discussion and understanding of the concept. So today's topic of discussion is seismic data processing, a case study from KG basin. So I'll start with the very basic, why seismic data processing is necessary and what it is. And so first I'll start with wait. And Rodiat, can you do one thing, that I'll remove this chat box from my screen, and you can turn it on, so that whenever a person asks question, you can forward it to me, or you can tell it to me that this person has asked this question, and so on. So because it will be a hindrance if I'll keep it here, so it will not be visible. The full slide will not be visible, so I'm removing it. Okay. So
yes, I can pick up the questions.
Okay. Okay. So before starting seismic data processing, we'll have to understand what is a seismic wave. So from previous classes or sessions, we have understand that seismic waves are nothing but the energy which travel through subsurface, and seismic waves somewhat looks like this. It's in a wiggle form, and we can calculate the wavelength of the seismic wave from this wavelength is equal to velocity by frequency. So if I know the frequency and I know the velocity, I can easily compute the wavelength. So so the distance between two crests or the two troughs is equivalent to a wavelength. Okay. So at any given point of time, the seismic wave looks like is in the form of sinusoidal wave, or in a zigzag pattern, and the maximum distance from the mean position is called amplitude. So this is the amplitude. We know frequency, we know wavelength, and we know the amplitude. So these things are very useful for interpretation purpose. So, and like when we do attribute analysis using OpenText and everything, so these parameters will be very useful. Okay, so this is the basic of seismic, how a seismic wave looks like, and its attributes like amplitude, wavelength, and frequency and velocity. Okay. So moving on to the next slide. So a seismic, see, in the previous slide we saw a seismic wave. Okay, but seismic wave are recorded in many formats, but the format which are used for processing is always in the form of seg-y. Okay, so it's always in the form of seg-y format. So it's always in the form of seg-y. So seg-y data is taken into the process in our system, and then we then we proceed with the seismic data processing. And always a seismic data has a file header, okay, which has the information of coordinate system and the location, and then the data itself, like amplitudes and everything. For trace 1, for trace 2 means for one short point, will have a file header which has the geometrical position of the each geophone. So it will have the geometrical information and then the data itself for each traces. Okay. So you can see here trace 1, trace 2, trace 3, and one file header. So this forms, now suppose there are n number of traces. So combining, could you please mute yourself? Could you please mute yourself? Please mute yourself. Please mute yourself. Kindly mute yourself. Yeah. So now suppose if I have n number of traces in a short point. Now I have a 8-channel short gather. Okay, 8-channel short gather. If I have a 8-channel short gather, so I'll have 8 traces for one short point. So if I take that 8 traces and combine them, then it becomes one FFID. So it will have a file header and 8 traces in it, and that will become one FFID or one first short gather or short point. Okay, data from short point one or short gather or FFID, first field information. Now, these are the recording media. As you can see here, earlier we used to have analog data, means it is recorded on paper and everything. But as the time passed, we started using magnetic tape or just like this hard disk magnetic tapes and everything, this round tape for storing the seismic data. Earlier, it used to be on paper, analog data were used were kept on paper. Please kindly mute yourself. It's very disturbing. Please. So I hope these are few examples of what do you call recording media. Okay, this one is the analog one, and rest are what do you call digital form. So or digital storage device. Okay. So and it has also evolved over the time. Earlier we used to have a magnetic tape. Data was recorded on a magnetic tape. Now we can record it on a pen drive or a hard disk or even a floppy disk or a CD compact disk. No, not important, but I don't know why I kept this. So I'll be moving now. So in previous sessions, we have discussed about the reflection seismic. So how it looks like, and this is a what do you call a simplified processing step, which we can see here, very simplified. So this is the seismic data acquired from the field. As you can see here, there are the amplitudes are there. There are 2 amplitudes corresponding to 2 reflectors. Okay, first one and then the second one. Okay, and since these are reflections that and we have discussed in the previous sessions that reflections are always in hyperbolic form, means as we move away from the short point towards the offset. So what happens is, as the distance increases, the time of data signal data recording also increases. So because of that, we get a hyperbolic what do you call reflection data looks like a hyperbola. And in the middle, you can see here, this truss is dead truss, means it's from top to bottom, it's ziggle form. So we call it dead truss. Dead means died, means it cannot be recorded. And this may be because of improper planting of the geophone. The geophones are not planted correctly into the ground. And because of that, this kind of traces are recorded. Okay, so we have to remove this, and we remove this by a method called trace killing. So even in seismic Unix, you can remove such kind of traces by giving a command like su, then SUR, and after that we just have to type trace kill trace or trace kill. So and you have to give the number of the trace. Like if this is the 4th trace, so you'll have to give the 4th trace, kill trace 4. So it will remove the 4th trace. So as you can see here, the 4th trace has been removed or killed. Okay, so we are left with only the actual data set. Okay, and after removing this, we combine the data set. Now suppose now suppose this is my reflection, just for the sake of understanding I'm saying, and this is my refraction or direct arrivals, just for the sake of understanding I'm saying. So when we do seismic processing, direct arrivals or refraction becomes subsidiary, or we can treat them as noise. So we have to get rid of the direct arrivals as well. Okay, so direct arrivals are always straight and reflections are always hyperbola. Okay, and refractions are also straight, but there will be a difference in angle. Now suppose this is my hodogram, this is the offset, and this is my time. So these are my direct arrivals, and this is my what do you call refractions, which we have seen in the previous sessions, and this will be my reflected data. So when we process the data, reflection seismic data, we have to only concentrate on the reflected phases and not on the refracted or direct arrivals. So we have to get rid of direct arrivals and refracted arrivals also. So, and that can be done. Now see, this was one single truss, so it was easy to remove just by using truss scaling. Now here are lots of amplitudes are there. Now if I want to remove, then how can I remove? So what we do is we apply top mute. Okay, so top mute is something like, now suppose if someone was talking, there was a noise. Now I was delivering lecture and somebody's mic was on. So when I was not able to talk properly or discuss or give the lecture properly, because I was getting disturbed by the noise from the some person's mic. So what I did, I just muted him so that his noises, his voice will be suppressed, and you can hear only my voice. Okay, so my voice is signal here, and the person whose mic was open, that becomes what? Noise, because of that voice you were not able to hear what I was saying. So what I did, I just muted that person. So here also we have, what we have to do is, now these are amplitude, this is also amplitude, and this is also amplitude, means these both are signals corresponding to a reflector. Okay, but when we deal with reflection data, or we only concentrate with the processing of reflected data, what we do is we remove the direct arrivals or the which are the noise, which acts as a noise for reflection seismic data processing. Okay, so after removing this direct arrivals, what we are left with, we are left only with the reflected data. Okay, sorry, what has happened? Why it's showing? Okay, so what happens once the mute was applied, and then we apply some filtering. Now again, here see, there are lots of here also there are lots of wiggle forms are there on the top, so if sometimes now here they are very small and amplitudes are prominent, but what happens in few cases, these wiggles will be large enough that the actual amplitude will be suppressed. So what we do is we apply some filters and everything to suppress those noises or random noise or coherent noise. Okay, and enhance the amplitude only. Okay, so what happens once the filtering and direct mute and everything was applied, what we do is we go for normal move out or normal move out. So what happens now, see, you can see here, as the offset is increasing, what is happening, the what do you call the amplitudes are getting in a hyperbolic fashion. So what we do is we in NMO, normal move out, in normal move out correction. So our aim is to bring all the amplitude in the same level. Like now suppose one amplitude is here, so we'll try to bring these amplitude on the same place. Okay, so what will happen, this is called normal move out correction. So in that, this is necessary just because when we stack the data, so it is required that all the amplitudes should be in the same place. Okay, so and this will help us to stack the data to enhance the signal to noise ratio and get a better picture, higher resolution of the image. Please kindly mute yourself. Okay. So that's why this NMO move out, normal move out correction is required to bring all the reflected amplitudes in one horizontal plane, as you can see here. And see, there is a what there is a slightly decrease or shift in the amplitude. That means there is a presence of fault. So this region and this region is faulted area. Now suppose what happens, I have a faulted zone like this. So the amplitude recorded here, 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 here. So the recording time for these surface will be somewhat lesser than the recording time for these this what do you call plane, because it's slightly lower than this plane, correct? So now suppose this is my surface and this is my for what do you call one of the subsurface, and then there is a faulted zone here, and because of the fault the same plane which was here has shifted to this particular place. Okay, so obviously when the ray will hit this and is recorded by here, is recorded by this geophone here, so the time will be slightly lesser than the rays striking here and recorded here, correct? So that is why we see a shift in the amplitudes. That means if there is a sudden shift, that means there is a presence of fault. So this particular portion has fault. Now, what we do is, now once we have applied NMO correction for the data and brought all the amplitudes in the same place, so after that we combine all the traces, means we add all the traces to get a stack section. See, after what do you call, after applying NMO correction, we have added all the traces, and because of this, now see here, amplitudes are not that much prominent, but as we what do you call, stack the data or traces, the amplitude becomes prominent, and this will help us in like suppressing any kind of noise or multiples. Multiples are also a kind of noise which are only what do you call, prominent in case of marine seismic data. Okay, not multiples are not that prominent on the land surface, but they are very prominent in land seismic data. Sorry, marine seismic data. Okay, so when we deal with the marine seismic data, we stacking becomes very useful because it suppresses or it kills the multiples or any other kind of noises and increases the SN ratio. SN ratio is signal to noise ratio. Okay, so I have already shown this graph or this image in our previous sessions. So you can see here there is a short there is a hole is drilled on the land survey, and explosives are put here, and then it is blasted and the wave travels from different layers and it is recorded by the geophones. And now see, in previous session, I talked about multiple corrections like static correction. Now here, what happens is, see, you can see how the top surface is highly undulated. Okay, so what happens is because of this undulation, also the time of recording becomes it varies. For even now, suppose if the geophones are only 2 meters apart, now one geophone is here, one geophone is here. But what happens is this geophone is placed here and this geophone is placed here. Okay, so that means if a wave reaches here and if a wave reaches here, so what you will see is that the time of arrival for this geophone is lesser than the time of arrival for this geophone because it's higher than the second geophone. So that is why, to remove the effect of this undulation, we apply seismic static correction. Okay, so static correction, what it does is it assumes a datum plane. Okay, or it assumes a datum plane, and it assumes that on that datum plane the geophones are placed on this datum plane, and we will see we'll discuss about static correction in next slides. And you can see here several types of waves, like see, these are the direct arrivals, which is not shown here. So this red which I drew, these are direct arrivals, and these are the refracted arrivals. And see, this one is the refracted one, this one. Okay, and this one is reflected one. And you can see here, sometimes what happens is the same we have in the previous sessions, we have discussed that the whenever a ray or seismic wave strikes any kind of interface, so some of the energy gets refracted and reflected. But in rare cases on land, it's very rare that you get a phenomena of multiple, or it's a noise. So what happens is, see, this single ray is coming here and it's going, okay, it's going up. But what happens is some energy gets reflected back, and then again it gets refracted and it goes to the geophone. So this becomes my what? This becomes my this become multiple. It's a kind of noise. So we have to remove these noises. Okay, and here, see, this is the long multiple, and here are short multiples. So how we can decide whether it's or differentiate, but whether it's a short multiple or a long multiple? So that can be differentiated by considering the depth of or the thickness of that particular layer. Now, suppose this layer has a thickness this big, and now you can see here in this particular layer only there are multiple small layers are there. So what happens is there will be multiple times that wave will get reflected multiple times, and then again it will reach the geophone. So that also causes a kind of noise in this actual seismic data. Okay. So now I have already given you an example between signal and the noise. So when I was talking, so that is signal because you are getting some kind of information. But if a person or some person switched on his mic or her mic, so what was happening? There was a background noise in that. Yeah, there was background noise in that. So yeah, there was a background noise, and because of that background noise, you were not able to hear me out, or yeah, you are not able to hear me what kind of information I was giving. So that particular thing becomes noise. So in seismic data processing, we have to get rid of the noise, but we cannot remove the noise fully, because if we will do that, so in removing the noise, sometimes what happens is signal is also get lost. So our aim during data processing is to keep the data, to process the data in some way that most of the signal is retained, and most of the noises are removed and most of the signal is retained. Any questions? No questions, then I'll move to the next slide. Okay. So what is seismic data? Seismic data is a set of logical algorithms applied to the data to remove unwanted part of the signal and retain only the data with actual signal having some information, or we can bring out some kind of information from that particular signal, okay, or data. So seismic data processing is to remove unwanted noises and keep the data with maximum amount of signal. Okay. And these are the processing steps of seismic data. Obviously, we don't. There are almost 18 steps are there, and, but we don't apply 18 or all the seismic data processing, because depending on the data or the reason where it was acquired, depending on that, we can what do you call it? If the data is cleaner, we can apply only few seismic data processing steps, and if the data is very noisy, then we can check where in which area the data was acquired and what kind of the lithology or geology is there in that particular area, and based on that we'll decide the what kind of processing steps we have to keep and what processing steps we have to remove. So nowadays we don't do this demultiplexing, because demultiplexing was done earlier. Now what has happened is, when earlier what used to happen is, like, whenever we used to acquire the data get multiplexed with because of the recording system. geophones and the recording system. But nowadays, because of advanced technology, better recording systems have been incorporated or are utilized nowadays. So the data acquired is already demultiplexed, and there is an option to choose in what format you want to acquire your data. So there is now we don't do this because it's already done during data acquisition. Earlier we used to do this, but since you should know, that is why I have kept it here. And then there is a trace header generation. I already discussed that Seismic data has a trace header or a file header, and then the data or traces. So how this is generated? So what happens when a data is acquired? Each geophone has a GPS embedded in that for the geographical location, so as to know at what coordinate the data was acquired, which is very important while loading the data. If you will not be able to give the location or geographical coordinates of the profile or your area of data acquisition, the data will not load and we cannot move forward with the data processing. So that is why what happens after the data was acquired, we do geometrical merging, which helps in trace header generation. Okay. So once the trace header is generated, the data is good for loading and move on with the processing steps. So then the third step is spherical divergence correction. So what happens in this? So what happens in this now? See, I use explosive for to generate the seismic data. So what happens as the data moves or goes down? So as it moves away from the short point, so what happens is there is a decay in amplitude. Okay, so that is so for that to compensate for that loss, we use spherical divergence correction to and apply some gain to what you call to amplify the amplitude. Okay, and after that deconvolution is applied. Deconvolution means like, now as I already said, now suppose if you are talking in a mic, what happens now? You are talking without a mic, so people cannot hear you. Okay, if you are addressing a large bunch of people in a big hall and you don't have a mic, so person cannot hear you from the only the people from on the front row, they can hear, and the people at the back, they cannot hear. So what you do is you take a mic and then you start talking in that so that everybody can hear. So what is happening? You are talking in the mic and the mic is amplifying your voice. Okay, so that is called convolution. Means your signal is getting convolved with the what do you call machine, and the convolved signal is then gets what do you call recorded or comes out as an output. Okay, there is a question. So please, I don't understand what you say. Done to improve the amplitude people. Okay. Okay. So spherical divergence correction. We apply spherical divergence correction to compensate for the loss of energy as the wave passes from the short point to the far off areas. And how we do that? We apply some gain. Okay, we'll be seeing what is gain. We'll see. We'll apply some gain. Okay, so this gain, what it does, it compensates for the loss of energy, and it makes the amplitude sharper for long offset. Okay, or for deeper reflectors. I hope I have answered the question. Okay, so now what happens is, so as this I was talking about deconvolution. So as the seismic signal goes inside the earth, okay, and then gets recorded by the geophone and then finally by the recording station. So what happens is, the when we blasted the explosive, the signal is generated and then it gets get inside the earth, and it gets convolved with the reflectivity of the earth. Okay, and with what do you call and the response of the geophone and the recording station. So what happens? The signal which we get has noise and also the unnecessary information from like gain is applied during the data processing, right? Yeah. We'll be seeing all these things in the coming slides. Here, just I am explaining the things so that you will be familiar as in what to keep it here. Okay. So we use deconvolution to remove the effect of convolution. Like when a seismic data passes through Earth, so it gets convolved with the reflectivity of Earth and response of geophone. So we have to get rid of the reflectivity of Earth and the response of the geophone. So we apply deconvolution. It's just the opposite of filtering or convolution. Okay. Here I have kept band pass filter. Okay. So in general, after deconvolution, we apply filtering. Seismic attributes come later. See, once you have processed the data and you have get a stack section, post stack migrated section, okay, then we will discuss about all these things in the coming slides. But see, seismic attribute analysis is done after, during interpretation, not during processing. Okay, and velocity analysis we will be discussing this in detail because it's one of the most tiring and time-taking and very important what you call step in seismic data processing. If you if you do any kind of mistake during velocity analysis, your stack section will be very erroneous and will not get a perfect stack section. Okay. Here I have after deconvolution we apply filter. Okay, there are different types of filters are there, but I have the bandpass filter because most of the time we get good result for with bandpass filter. So see, I am giving only the superficial and the concept of seismic data processing because you cannot cover this seismic data processing in 1 hour or one session. Okay, so I'm just giving you the basics or the fundamentals so that you can go and read the books which I have suggested, and you can understand fully, and you can read yourself and you can understand. Then comes the trace normalization. So I have already talked about trace normalization. What does it mean? If you have a dead trace, so removing those kind of dead traces which are basically a noise and doesn't help in our goal to get some information, so we have to remove those noise. Could anyone please list the books that have been suggested? In the first session itself, in the what do you call it, the presentation I shared with the moderators here, there is a slide with the 5 books which are easily available online. You can get those books and you can read. Okay, and then after trace normalization and everything, we do velocity analysis. Velocity analysis is very tiring because now suppose if your velocity analysis is wrong, so you cannot do the normal move out correction. Normal move out correction is, I have already talked in the second or third slide where I told you that suppose if a reflected phases look like high, so we have to bring all the amplitude in a flat horizontal layer. So that is called normal move out. So if your velocity analysis is incorrect, you will not get normal move out correction will also be incorrect. And once this normal move out correction is done, we go for CMP stack. We combine all the traces for a common midpoint or common depth point. I have about types of seismic data acquisition like CMP, CDP, and everything. So sorry. Okay. So after move out correction, now suppose if my velocity analysis is correct, so our normal move out correction will be also correct, and then we can go with CMP stack. CMP stack is nothing but the combining of all the traces, okay, or adding all the traces to enhance signal to noise ratio, okay, for one CDP or one CMP or one FFID, you can say. And actually static correction is done in the at the very beginning, but since for marine seismic data, because I'll be discussing about marine seismic data, so static correction is not required there, so that's why I have kept it here. But for land, seismic data processing, static correction is always done at the very beginning. And then we do dip move out correction. So what is dip move out correction? I have already discussed this in the previous session that now the Earth's surface is not horizontally flat. Okay, so it will be having some dipping. Okay, so because of that, what happens is like my image of the dip section will be, or the dipping layer will be very erroneous in the stack section. Okay, so for that we apply migration to bring the what do you call pseudo dipping reflector to its actual position. Okay, so for that we do dip move out correction, and then again we do velocity analysis for such scenario, and then we do DMO stack, matlab dip move out stacking. So once the dipping, I have discussed this dip move out starting in the previous section when I was talking about the CDP and CMP data acquisition for flat and dipping layer. Okay. So then we apply this DMO stack to combine all the traces for one dipping layer. Okay. And then after this we apply some more filter to remove random noises and attenuation or ground roll. Okay. And after that, again deconvolution. Once the stack is prepared, then we do FK filtering. That means frequency and wave number deconvolution. Okay, to get the to remove the what do you call? Now suppose you have removed most of the noises, but still my stack section is not looking crisp and perfect. So what we do is we apply some deconvolution after stack is prepared to remove to get rid of all those noises which are left even after removing most of the noises. This is not required, and I'll not be discussing this, but this will be in the book, because see, I have not done this, and but there was a in one of the book it was there, and I had no time to go through this, so I'll have to read. I'll have to look for this. Okay. So time variant filter. Okay. So do one thing. It's your responsibility to tell me in tomorrow's class what is time variant filter. So look it up in Google or book, and then tell me. And then we do migration and scaling. This is this is the final processing step. Okay. And even after this, if something remains, then we can again go for time variant filter migration. Again, we can apply migration and then scaling. Okay. But these three are not that important. Most of the processing steps and here itself. Okay. Because we get a crisp stack section. I have already discussed this. Nowadays, this is not so important. Okay. So this is not important nowadays. Now the data is acquired in a demultiplexed form itself. So I'll not be discussing this. I'll move forward to next. Trace header generation. I have already said that trace headers are generated using by applying geometrical merging. Okay, and because each geophone has one coordinate system associated with that particular geophone. So for each geophone, there will be one trace, and each trace will have a trace header and the data. Okay, so it gives a unique identification for each trace. Okay, now when we combine the data for that particular short point for all the geophones, okay, one short point. So that becomes my one shot gather, and we collectively generate the trace header for that particular short point and the collection of geophone associated for that short point. Okay. Here it's showing how the short gathers are generated. See in this, in the upper section here, this is called trace header, which has only coordinates and the recording length, sample rate, sampling rate, what was the sampling rate, what was the sampling interval. Okay, so all the information will be here, and then there will be traces, and traces. Okay, so that's it. Next. Here is a example which we have discussed in the previous sessions itself. So we have receiver shots, and then we have a receiver. So it's called common receiver gather. We generally don't do this, but this is the most common type of seismic data acquisition uh, parameter or seismic data acquisition what do you call it, set. Okay. So CDP or CMP, common midpoint or common depth point. So one of you guys asked me what is spherical divergence correction. So what happens? I have already discussed this. As the seismic wave move away from the shot, what happens as because see, energy loss is very minimal in a perfectly elastic media, but since there is no such thing as perfect elastic media, it's just a hypothetical assumption. So an Earth is perfectly inelastic. So what happens is as the wave passes from the short point to the geophones, as it moves away from the short point. So what happens? It reduces. There will be a decay in energy, and because of that, amplitude decay will also be there. And to compensate for all those things, we apply this spherical divergence correction, and we apply some gain function to improve the amplitude or to enhance the amplitude. The number of students are decreasing. Is my talk is boring or something? Anyways, now we have the basic purpose of spherical divergence correction is to what? To enhance the energy and the amplitude so that amplitude corresponding to each reflector can easily be picked, okay, on the seismic section, and then from that will be able to delineate how many subsurfaces are there corresponding to each reflections. Okay. Now, see, as you can see here, now suppose the energy is generated here. So you can see here there is a peak in the amplitude, but as it moves away, now suppose this can be taken as time, and this can be also taken as offset. So what happens? Amplitude is decaying as the time is increasing, or the offset is increasing. So what happens is we apply some gain, okay, to compensate for the loss of energy. So you can see here, this is the gain function which we apply. We are enjoying the lecture, so the depletion might be due to the poor internet connection. Okay, great. As you can see, please mute yourself. See, here you can see here the amplitude is decreasing, and so there is if I want to draw a curve, how the amplitude is decreasing. So we see exponentially, the amplitude is decreasing exponentially. So we have to apply gain in similar fashion so that it compensates for the loss of energy. So you see here, the amplitude is decaying in this way. So we apply gain in this fashion. So what happens? The outcome will be this, the middle portion. So what happens is that amplitude for the decaying portion or for the deeper reflected getting enhanced. Okay. Now here, see here the amplitude is decreasing has decreased very drastically, and we have applied gain. So what happens? This amplitude again becomes prominent. Okay. So with this, we will be able to differentiate that, okay, there is also a reflector here, and a reflector here, and a reflector here. Okay. This can only be possible by applying gain. If I don't apply gain, that means the energy is decaying, and I will not be able to differentiate whether there is an amplitude or not, and or reflector is present or not. So this will lead to what you call erroneous seismic data processing, and the delineation or depth delineation of the layers, or the depth of the layers will be erroneous as well. Okay. So this is what I was talking about. Now see, this is my reflected reflection. Okay. So I did my velocity analysis, and my velocity analysis was correct. So what happens is all these reflected phases come into one horizontal plane. Okay. And now suppose if I pick velocity incorrectly, so what happens if I pick wrong velocity or lesser velocity? So my amplitude will increase, will go up. Okay. So this is this is incorrect. And if I pick during velocity analysis, if I pick higher velocities, so what will happen again? My stack section will be very bad. Okay, because there again there we are dipping kind of thing is happening just like here, just like here. So, but if my velocity analysis is perfect or correct, so we'll get a perfect saturation. All the amplitude will come into one line. Okay. Rodit, I think I'll have to take 2 more classes or because it's very difficult. It will be very difficult to impart everything. So let's see if I'll be able to complete by tomorrow. It's fine. Otherwise, we'll increase the number of classes. Okay. So pre-stack analysis. Pre-stack analysis means before stacking the seismic data in the previous C. Once the all the amplitude has come into the in one horizontal plane, what we do? We stack this seismic data, and we make only this will be added, and will get only one trace. Okay. So see here, the amplitude is not that high, but if after stacking, so what is happening here? Constructive merging is happening. So what happens is all the amplitudes get added up, and we get a very prominent amplitude here. Okay, so this becomes this is called stacking. So pre-stack analysis are like, I have already said that. Pre-stack analysis is like filtering, deconvolution, muting, and velocity analysis, and then NMO correction. And if my velocity analysis is correct, then we go for stacking. Okay, so this is called pre-stacking analysis. Okay, so I have already discussed this in the previous slides. So I'm not going to read out all these. So this will be with you guys. You can read it, and you can hear. You can read it by yourself. I just for the sake, because once I'm done with the presentation, still you should have this so that you can read and you can understand. That is why I have kept it here. This is again pre-stack analysis of what I have already discussed. Now in marine scenario, we have to remove multiples also. So what happens is, how can we identify multiples in case of marine data? In land data, it's very difficult to identify multiples, but after stacking, most of the multiples are removed. But in marine data, what happens is, now see, the streamer is on the water surface, and the air. One second. हेलो मम्मी, हम क्लास ले रहे हैं, थोड़ी देर बाद बात करते हैं, 1 घंटा बाद फोन। So what happens? Air gun is there, so the air gun will blast some air bubble with pressure, so there will be water column up to here, and then there will be surface. Okay, so the air bubble will go with the pressure, and then it will hit the surface. Okay, so what happens in for marine scenario? Now suppose the first data is recorded at 2 milliseconds. Okay, so the multiple is always present at the double of the first data recorded. Now suppose the first data, the time of recording time is 2 milliseconds from first reflector, then the multiple will be at 4 milliseconds. That means the multiples are always at the at double the time. Okay, now I hope I'm able to explain in a way that you can understand. So if for marine seismic data, I can easily identify multiples, and we can remove that those multiples just by stacking the seismic traces. Okay. If you have any question, you can ask, or we'll move to the next slide. Okay. I have already where is my pointer? Okay. I have already discussed this in the first slide itself. Now see, this is my direct arrival, and these are my reflected arrivals. Okay, and this is my dead trace. So I applied what? Trace killing. I removed this, and then I applied top mute or front end mute. Sorry, front end mute. Okay. So top mute. We applied top mute to remove this. We can also apply bottom mute to remove multiples. Okay, we can we can apply surgical mute to remove ground rules or any kind of dead traces in between because of one bad reflector. Okay, so after applying mute and trace killing, we are left with the reflection data only. and that can be used for further processing. This is all pre-stack analysis. I have already discussed this. And here is a chart of pre-stack analysis, which you can see and you can read by yourself. So I'm not going to explain all these things because I have already explained. And if you have any question up to here, please let me know, or we will move to the next slide. Shall I move to the next slide? Okay. So what happens? Why static correction is important? I have already discussed that the subsurface, or sorry, the top surface of the earth are very highly undulated. But what happens is, like most of the time, we look for a surface which now suppose I planned a survey, seismic survey for oil exploration. So what I'll do is I'll read that petroleum geology book. Okay, which area can be most what do you call highly probable for finding oil and gas. So I'll read about that area, and then I'll plan my survey, and then I'll go for preliminary inspection. So if my land is flat, then there is no problem. But if my land is highly undulated, so what happens is the geophone distance, planting of geophone will be uneven. And one more thing is, like, now suppose if the land is flat, so and if I want to plant my geophone at regular intervals, so I can easily do that for wired, even for the wired connected geophones. Okay, but because if the land is highly undulated like this, so this regular interval of 5 meters will not be maintained, because what will happen now? Suppose one geophone is here, and then there is a upland, and then so what happens? Each geophones are connected with wires. So what will happen? My next geophone will be planted here, and the distance between them will be less because of this undulation. So that also causes some problem in the data acquisition. So what we do is we mostly for the undulated surfaces, and to maintain the regular interval of the geophone, we use wireless or codeless geophones, okay, which can be charged by solar energy. Okay, but what about the undulations? Regular interval I took care of, but what about the undulations? So in that scenario, I apply static correction. But static correction is not only for the undulations. Now, top layer is always highly weathered layer. Okay, so that is why what we do is, when we acquired the data, we look for a place which is where the geophones can be planted very formally. Okay, and now suppose if the subsurface is weathered, the geophone plantation will be very will not be solid, and if I blast the explosive, and there will be vibration of the ground, and the data is recorded by the geophone, what will happen? The geophone is, since the geophone is not planted firmly with the ground, and so geophone starts shaking along with the ground. The ground is still shaking, and the geophone will start shaking on itself. So that also causes the dead trace, or some kind of noise in the data. So to compensate for all those things, we apply this static correction. So in static correction, what happens? The elevation difference among the traces. See, one geophone is here, one geophone is here. So traces will also, with time of acquisition for these two geophones, will be different, which we will see in the next slide. Okay. So what we have to do is, we have to remove the effect of these undulations, and we'll assume one datum plane, okay, which is static, okay, and which is just an hypothetical plane, okay, and we'll try to compensate for the this depth. Now suppose one geophone is here and one geophone is here. So what we'll try to do is, we'll use some algorithm, mathematical algorithm, and we'll try to bring this geophone to this level and this geophone to this level. So now what happens? Now both of my geophones are on the same datum plane. Okay. And also, since the top layer is always weathered, so it will have energy decay will be higher, because of compaction is not there. See, we already know that seismic wave, or any kind of sound wave, travel faster in a highly compacted media. Now, if a media is highly weathered, so what will happen? There will be energy decay of energy will be high. So we'll have to compensate for that also. So for static correction, we have to take care of all these parameters, and then we can go for static correction. See, and for static correction, I already said that. Now, suppose if this is my datum plane, and one geophone is here, one geophone is here, and time of recording for this geophone will be different, and this geophone will be different. Basically, this should be the traces should reach this geophone first, because this is the first geophone. But what happens? The traces are reaching this geophone first because it's slightly lower than the first top wala geophone. Okay, so we compensate using this formula. So del TS is the source correction. Now suppose source is like this is also a highly undulated area, which we have seen in the first in the starting. We have seen an image of short point and the data acquisition, and my short point is here, and I blasted. So I have to take care of the source correction for the source and for the receiver. Okay, and the addition of all these two will give me the total correction, which we can utilize for to make the undulations into to bring the undulation into a one datum plane. Okay, okay. So now my geophones are the short points are in one datum plane. Even we have to take care of the short points. Okay, so we'll have to bring the not only the geophone but also the short into one single datum plane. Okay. So as you can see here, this is my surface. Okay, you can see this is the short, and one geophone is here, and one geophone is here, one geophone is here. So what happens is my time of acquisition will be different for all these geophones, or the time of acquisition of the or receiving of the traces will be different for these geophones. Okay, and that will have that will create problem during the processing of the seismic data, and will get a very wrong stack section. Okay, because NMO and normal move out corrections and everything will be erroneous. So what we do is we choose one datum plane. See, this is the top surface and this is the first layer. So, and this is the weathered layer. So that means LVL. LVL is low velocity zone, because low velocity zone means the velocity of the seismic wave is low in that particular layer or zone. Okay, so that becomes low velocity layer, and this is because of the presence of a weathered layer, or the compaction is not that, or cementation is not that good, or presence of any kind of quartzite material. But generally, quartzite and everything are found much below the subsurface. On the top layer, this LVL is only because of the weathering of the soil. Okay, moving on to the next slide. See, this is a stack section. Now, we saw in the previous sessions, we have seen the traces. It's only the traces, but this is a stack section. So see, this is a stack section, and you can see here how noisy this data looks like, right? You are not able to make you are not able to make differentiate between different layers. See, if I believe this is one a reflector, and this is one reflector. Okay, but this is not that clear, and again some reflector are here like this, but this is not clear. But in this, after we apply some kind of all the, like, we have applied all the processing steps, and then we have come up with the stack section. So we can see here the reflectors are very prominent in this, very prominent in this, okay, very prominent in this, and this is see, this was the stack section, but this is the traces for one for see, this can be called as one FFID, combination of multiple CDPs. See, this is for one CDP, this is for second another CDP. So combining all these things becomes one FFID, or one short gap. Okay, and this is also after applying the datum correction, I guess, after applying a static correction. So you can see here the reflections are prominent. The reflections are prominent. reflections are prominent. So you can see here also. And here also you can see here the reflections are not that good, and this may be because of some kind of noise. Noises are taking over the actual signal, but signals are prominent in this particular area. In this particular area. Okay. Now I have already discussed what is deconvolution. Deconvolution is just the opposite of filtering or convolution. So when a seismic wave passes through subsurface, so it gets convolved with the reflectivity of the earth and the response of the geophones, and so we have to remove these two effects of earth reflectivity and geophone response from the actual signal, and that makes that is what is called deconvolution. Deconvolution is also called inverse filtering. So what it does is it enhances the signal by compressing the amplitude or making the amplitude sharper. Okay, so deconvolution will give me the amplitude due to all the reflectors during deconvolution. Amplitude due to all the reflectors will become very sharp and will be able to easily differentiate or delineate between different multiple reflectors. Okay. Here also, these are just the what you call theory. For you, I have kept, but basic concept I have discussed. If you will have any question by reading this in future, you can write it to me on my email address. I'm not going to discuss this because of the time, because we started late and we have to cover many things. See, in deconvolution, this is not important. You can understand by yourself. If you have anything, see, this is the geological section. This is the geological section, cross section of geology beneath the subsurface, and this is the impulse response of the earth. Okay, and this is the seismic trace. So the seismic trace acquired. So it's a combination of what? Combination of this this reflectivity due to this geological formations. Okay, and the response of the geophone. Okay. So the traces, seismic trace we get, it's convolved with the earth response, impulsive response or reflectivity, and the response of the geophone. This I'm not going to discuss. I have already said that in deconvolution, what happens is the amplitude gets sharper. This is just for you guys. You can read it and you can understand. If you don't understand, you can always reach out to me. So I'm not going to discuss this. This is just for your basic understanding. If you read this, you will understand. Okay. This is just the part of deconvolution. And deconvolution can be, see, before I have already discussed about the convolution. So for understanding the convolution, it can be done in frequency domain and time domain, but it's always better to do in time domain, because in time domain it's just simple multiplication. But when you go for if you do convolution in frequency domain, because in many places they ask question regarding convolution and deconvolution. Okay, so first I will give an example of what is convolution and cross correlation and everything. So this is this cross correlation. Okay. So what happens is we generally do this convolution and deconvolution in time domain. See, I have the data in frequency domain, but data is always acquired in frequency and time domain. Okay, both. Now, some places we use frequency domain for processing, and in some places we use time domain. Okay, and the conversion from time domain to frequency domain and frequency domain to time domain can be done by using Fourier transform function. Okay, FFT or fast forward Fourier transform. Okay, so it's a very simple concept that you can read about Fourier theorem. Okay, and why it is important, and in signal processing or seismic data processing, and how we can transform signal from frequency domain to time domain using Fourier transform, which you can read it from the book. So convolution, correlation, and what you call autocorrelation, I'll be discussing now. See what happens now. These are, you have two traces. Now suppose trace 1 and trace 2. Okay, so what happens generally. To understand the deconvolution, first I'll talk about cross correlation and convolution. Sorry, autocorrelation and cross correlation. So cross correlation and autocorrelation are only done are mainly done in time domain, and convolution is done in frequency domain. So in frequency domain, convolution is just multiplication, but when we talk of correlation and autocorrelation, to understand the deconvolution, we do that in time domain, because our math related to this becomes very simple, because we'll have to just multiply. Now see how many data points we have. 5 data points we have for trace 1, and 5 data points for trace 2 as well. And we see here the data for trace 1 is different than from the trace 2. So what we do is we do cross correlation, because see, we are using 2 different traces. See, now suppose this is my signal, and this is my signal, and this is my impulse response of the earth. Okay, just understand. So what happens is, if I want to do cross correlation, so what will happen? I'll keep one trace fixed, and then I'll move the other trace in such a way that the last of the second trace always falls beneath the first information of the second of the first trace. Okay, and then we'll move backwards. Okay, until this position is just falls beneath the first digit falls beneath the last digit of the first trace. Okay, so what happens is we'll have 4 lakhs, because there, see, the number of times it will move will be only 4, because the first time first digit of the first trace falls beneath the or first falls above the last digit of the second trace. So in cross correlation, what happens is we multiply this and then write. So here it's 2 and here it's -1. So what will be the output? -2. So we write this, and then this moves one step back. So now -1 falls here, and the -2 and this falls here. So what happens? This multiplied by this, so we get -1, and this multiplies by this, so we get 2, and then we add those things. So what will have 2 minus 1 becomes 1. Okay, so similarly we'll sample all the digits of both the traces, and will be left with this output. And we can see here maximum cross correlation is happening, that is 6 is happening for lag 2. That means only 2 places are left for this. Oh, sorry, here left for this. Okay, so lag is nothing but the amount of the spaces left. Okay, so this is cross correlation. Similarly, auto correlation is done. Like, see, if I have a single trace only, or if I want to compare the two same trace, so what we will do is we'll multiply the same trace in same fashion as we did here, and then we'll get auto correlation. So why it was important to understand cross correlation and auto correlation? So if we know the effect of this where is my pointer? Yeah, if we know the effect of this cross correlation, convolution, cross correlation, and auto correlation, so we can easily remove the effect of this to get the deconvolved data. Now this is my output of the convolved data, or the cross correlated or auto correlated data. So I can remove the effect of these from the actual signal. Okay, and my output will be much crisp. Okay, so this is just the example of the same thing. And see, here also this is a real-time data set. You can see here these are the direct arrivals, and there is one reflector here, and another reflector here, and another reflector here. Okay, so, and again, this can be treated as multiples, because if we check, If now suppose this is 2 milliseconds and if it is 4 milliseconds, this can be taken as multiple. So and we can ignore that. Okay. So and you can see here this is the ground rule. This is ground rule. So ground rule is either can be removed by deconvolution or filtering, or even by surgical strike, surgical muting. So what we do is in surgical muting we will, where is my pointer? Where the hell is my pointer? Okay. So in surgical strike, surgical mute will remove this full ground rules. Okay. But it should not be done because our data will also be lost. So I have talked about mute. Mute is nothing but removing the traces, unwanted traces fully. So this is front end mute and surgical mute. There is also called this is also called top mute. Okay, and then surgical mute is there, and then one more is there. That is bottom mute. So for reflections survey, we use top mute for land survey, and we use top and bottom mute for marine survey. In bottom mute, what happens? We can remove effect of multiple using bottom mute. We can remove totally. Okay, like now suppose if someone has cancer, so what doctor does? Like it cuts out the cancerous cell and out of the body. So mute does the same thing. It will weed out the unwanted noises from the seismic data. So see, this is my these are my direct arrivals and some kind of noise. So I use top mute and I remove. So in this you can see I have removed the effect of the these noises. Okay, and I'm left with the data. Even see for this is the land data, so that is why they have not removed the direct arrivals also. But for marine data, we'll get rid of this also. So we'll apply top mute like this. We'll select the now suppose this is my first reflector. So we'll select this first reflector and we'll apply top mute, and it will remove all other amplitudes after or above the first reflector. Okay, this is an example of surgical muting to remove ground rules, and this is due to the unwanted. Now suppose if a reflector is very noisy, so we can remove that also. Now coming to velocity analysis. In velocity analysis is see there are different types of velocities. Okay, there is instantaneous velocities. Okay, at particular instant. Then there is interval velocity between the two layers. Then the average velocity of the same particular layer, and then root mean square velocity. Okay, and then there is NMO velocity, which is used for NMO correction, and then stacking velocity, then migration velocity, and then apparent velocity. So in velocity analysis, we take care of all these things, and this is very important. Like generally, we focus on the NMO correction for a flat horizontal. If I have a marine data, so we only do NMO velocity analysis or velocity analysis for NMO correction. But if I have data from land, so we also apply for. We also do migration velocity. We apply migration velocity or dip move out velocity for dip move out correction. Okay, this is just the what you call explanation of all the velocities which I already said in the previous slide. So you have to go through. And now coming to the main or very important image. Now see, this is my data, and in this they have not removed the effect of direct arrival. So this means this is the data from land data. Okay, so they have kept the direct arrivals, and then there are reflectors. So what happens once the NMO correction and everything we have to apply before applying NMO correction, we go for a velocity analysis. So we apply velocity analysis, and the thing which you see here is called velocity semblance. And in this we have to pick the brightest spot corresponding to each reflector. And if even if we miss by micro milliseconds, so our picked velocity will be incorrect, and the NMO correction will be also erroneous, and the stacking will not be possible, or our stacking section will be incorrect. So as you can see here, these triangles, they have picked velocity corresponding to each reflector or each reflection, which we will see for actual data also. This is taken from Ilma's book. Okay. How many students left? Okay, thank God, 6. So velocity analysis, I discussed. This is very important and this is very time taking because you have to do it for all the FFIDs, and you have to be extra careful while picking the velocities. Okay. So, and you can read about velocity analysis from Ilmaz or other books in detail. Okay, because we don't have that much of time. So that is why I'm just skipping all these things. Velocity analysis, you can read here also. And velocity analysis gives us actual velocity of the reflector, which helps in bringing all the reflected amplitude into one horizontal plane. And then we can go for stacking or CMP stacking to get a stack section. Then we apply migration or FK deconvolution to get a stack section or actual thing. Okay. These are the factors which affect the velocity estimation, the spread length, stacking fold, okay, signal to noise ratio, muting, and these are all things which we did just discussed about. These all affect our velocity analysis. So we have to be very extra careful while processing seismic data because each step will have effect on the velocity analysis. Okay. And after once the velocity analysis is done, we do stacking. And why it is important? It helps in improving signal to noise ratio, and it also what it does. Stacking what generally does is it brings all the amplitude to zero offset. Okay, I have talked about the zero offset thing in the previous sessions. Okay, and it reduces the data, means it removes most of the noises. It attenuates or it kills the multiples, and it also gives actual velocity information of the reflectors. Okay, these are the types of multiples which I was talking about, which you can find in the books. Okay. Now, I have already said that. See, what happens is, I said that you can remove multiples by stacking. So now this is my reflectors or reflections. Okay. So after velocity analysis, I applied NMO correction and I brought all the amplitude into horizontal line. So here it was in hyperbolic fashion. Here it is in one horizontal line. But what happened to the multiples? See, this will be applied to all the true amplitude, means corresponding to each reflector. But if multiples are present, that this NMO correction will not be applied to this multiples. So what we'll do, we'll apply bottom muting and we'll remove this. Okay, so our data is now devoid of multiple, which is a noise, and we are left with only signals. And this is a migration. There's a very good what do you call video on YouTube by some Pakistani professor explaining migration and why it is important. You can see that video with the help of what do you call animation. He is trying to explain. So see, now after see, this is the pre-stack migration. Like before making the stack, see, when we do stacking after NMO correction or deep move out correction, then we do stacking. So this is pre-stack migration. This is post-stack migration. After stacking all the data, we migrated the data, and here also, here before stacking we migrated the data. You can see here the reflectors are prominent in some reflectors are prominent in this, and some reflectors are prominent in this. So both these data types are very useful for like when you interpret the data, like for attribute analysis and everything. So what are migration? Migration I have discussed in the previous session. This is just the theory which you can read and you can understand. Okay. This is, the image is not clear for, and I could not find a better image for this, so sorry for that. Here here you can see why migration is important. Now see what happens. This is my actual surface, okay, and these have undulations. Okay, So what happens? See, and this is my, now suppose my geophones are planted here. So what will happen? The time taken by this trace to reach here will be less, and the time taken for this will be more. So what will happen? So here, see, there is a, this is my actual reflector. But what happens here is there is a formation of a bow tie. What is a bow tie? This is called bow tie kind of effect is happening. Okay. So that means my actual reflectors have not been imaged because of this bow tie effect, and we have to remove the effect of these bow tie to get the actual reflector. And because of that, migration is important. We have discussed the mechanism of migration in the previous session. You can refer to that video. Here also the same phenomena is happening, but images are not clear, and sorry for that. I could not find a better image. Types of migration. So here you can see there are different types of migration, which you can read it on yourself. So, but two types of migration are very important. So two types of migrations are very important for data processing or interpretation. So one is time migrated data and depth migrated data. Sometimes time migration data gives better resolution, but in most of the cases, depth migration migrated data gives very high resolution of the stack section. So we do both. We do time migration, we do depth migration as well, and we compare which one is giving me better output. So we keep that. Okay. This is one example of time migration. This is an example of time migration. Means that we bring the event not from not at the place it was recorded, but it occurred. That means we try to bring the response of this recording station or geophone, not the place at the not the place where it was recorded or the energy was recorded or signal was recorded, but where the actual signal took place. Okay. And this is pre-stack depth migration. Okay. So we see here depth migration is giving me a better result than the time migration. Okay. So that is why most of the time we go for depth migration, but in some cases we time migration also helps. Okay. So migration principle, this is for you to read. If you'll ask me, then I'll explain. Otherwise, I'll move on to the next slide. This is also migration principle, which I have already discussed in the previous slides. Okay. This is the math behind the migration. And this is also has been discussed in the previous slides. And this is now this is the subsurface model of the now suppose I processed the data and I came up with a model, so I got this subsurface model, and but this is erroneous. But when we go for a zero offset time section, that means I have brought all the amplitude into zero offset. Then that will it has been migrated well. Then that means correctly, if it has been migrated correctly, then we'll get to the actual image of the subsurface or reflectors. Again, migration principle. Again, see here, you can see the bow tie effect very clearly here. Here it's happening. Here it's happening. Here it's happening. And for the reflections corresponding to these, this, and this is the mechanism just for you to understand. Here the image is not clear, but I'll draw. This kind of bow tie effect is happening here. If you have any question here up to here, they can ask me, or I'll move to the next slide. This is also the same thing. Before migration, the data, how the stack section changes in resolution. See, this is before migration. You can see here multiple bow ties are visible, but once the migration is applied, the reflectors are brought to their actual position, and the effect of bow tie has been reduced. Okay. See, it's showing the bow tie effect. Here also you can clearly see the bow tie effect, and after migration it has been suppressed. And this is Kirchhoff migration. This is done after once all the dip move out correction and all the migration. Now suppose in some cases normal migration doesn't work. So in that scenario, we go for Kirchhoff's migration or FTD convolution and everything. And you can what you call refer this in the book. I'm not going to explain because we have very less time left, and I have to discuss what you call the case study as well. If you have any question, you can ask. I'll explain. Otherwise, I'll move because these things are Kirchhoff's migration is a kind of migration which you can read from the book, and the main thing is that the concept of migration is clear. So that is the most important thing, and then we can move. And types of migration, types of filter, and types of deconvolution, you can read it by yourself. Okay. Again, here the Kirchhoff migration, Kirchhoff migration, Kirchhoff migration. Okay. Now here the effect of bow tie is very prominent, as you can see here. See, this is the raw data, and you can see there are many bow tie effects are happening, and this is 2D migrated data, and the effects of bow tie has been removed. And you can see here, this is the actual position of the reflector, but here we are getting a very erroneous reflector position. This is just because of the what you call dipping and bow tie effect. Bow tie effect. Bow tie effect. Okay. Migration domain. Now, this case study I'll discuss. I hope this seismic data processing steps are clear. These were the only main steps. Okay. And then you can apply the same thing, because once the concept is clear, you can apply the same thing in seismic data, seismic Unix, and you can process this data. And while processing the data using seismic Unix, you can get the data from the same site. And while processing the data using Seismic Unix, if you encounter any kind of problem, you can write to me. I'll assist you with that, because you just have to remember the command. Okay, and each command starts with SU. SU means Seismic Unix, and then the command. Now, suppose if you have to apply mute, so write top mute for top muting. For bottom mute, you write bottom mute. Okay, so it's like that. So, and you can get the manual and everything you explained in that manual. You can just take the command from the manual and you can apply and you can learn. Now, this case study, I'll take 5 to 10 minutes and I'll complete. And this is the processing steps which I have already discussed here. I will be showing that. So this case study is from KG Basin, that is Krishna Godavari Basin. Krishna Godavari are the two rivers, and so they form a basin. And the huge amount of gas hydrates are available there. These are some these are some places where gas hydrates are available, and these zones are called EEZ, in exclusive economic zone. And you can see here the gas hydrates are present around the coastal areas of each country, most of the countries. Okay, so gas hydrates are only found in marine scenario. And since I was working on gas hydrates, so I worked on marine seismic data processing to delineate gas hydrates. So what are gas hydrates? Gas hydrates are nothing but the combination of any hydrocarbon, or mainly methane, or carbon dioxide, or ethane, and water molecule. So when a hydrocarbon molecule mixes with water molecule, they form clad threads or gas hydrates. And they have very high energy values, like 1 cubic centimeter of gas hydrate can produce 160 cubic centimeter of gas. So we get huge amount of energy from less amount of gas hydrate. So it's a kind of non-conventional future energy. And the formation of this, these are always found in the coastal areas or shelf areas of the continental shelves, and they form under very specific temperature and condition, which is given here. And if the temperature and pressure conditions are even slightly less and more, so the formation of gas hydrate will not be that will not be possible. Okay. So factors affecting gas hydrates, like thermodynamic regime means pressure, temperature, and migration of the hydrocarbon carbons, composition of what kind of gas is present there, whether it is methane is present below surface, or carbon dioxide or ethane. So on that also, salinity and porous structure of the porous media, lithological characteristics of that particular area, and geothermal gradient means what is the geothermal radiation in that particular area. Okay. But how do we identify gas hydrates on the seismic imaging, or sorry, seismic section or stack section? So what happens is, whenever there is a gas hydrate present in subsurface, and we image that subsurface with seismic data. So what will happen if there is a presence of gas hydrate? So gas hydrate always entrap gas, natural gas. So if a gas hydrate is present there, just below that gas hydrate, the reflectivity will be very high on the seismic section, and also the gas hydrate will mimic the or the top surface of the or ocean bottom. So that is called bottom simulating reflector. So if we find a reflector which is mimicking or aping or copying the seabed, that means that particular layer has gas hydrates, and it is gas hydrate are always associated with higher reflectivity. Okay, that is because of the presence of gas hydrate, natural gas. The processing steps I have already discussed on the top, so I'm not going to talk again here. So this is the raw data. This is one of the FFID. I'm not showing all the FFIDs, just I'm showing one of the FFIDs, and I'll be showing only one of the FFIDs, FFID for processing steps, because the image will become very small. That is, I have not included all the FFIDs. So you can see here, this is the raw data, and you can see this is the direct arrival, and you can see here how the data is, how noisy the data is, and you can see the reflectors are not that prominent in this raw data. Then what we did, we applied band pass filtering or trapezoidal filter or any kind of filter. We suppress the noise. So you see here, these noises were suppressed. One second. Pointing option. Okay. So these noises were suppressed in this section. This is the after applying band pass filtering. Okay, and also you can see here the reflectors are not that prominent after applying filter, and there is but the direct arrivals has become prominent. So what we do, we'll apply mute. See, this was the filter data. The data which was filtered, it's shown here. I have zoomed the data just to show you clearly the effect of muting. So this is the direct arrivals, and these are some bad traces. So to remove the effect of bad traces, what I did was, like, I applied top mute by picking the first reflector. See, in this image, the first reflector was prominent. This is the unzoomed version, but here this is the zoomed version. So I picked the first arrivals or first reflector, and then I applied top mute. So now you can see here the effect of direct arrival, and everything has suppressed, and the data has become, the ability has become more clearer. Yeah, any question? Any questions? No questions. Okay. See here, the amplitudes are not that prominent. That is because of the effect of direct arrivals and these back traces. But once we apply the top mute, the amplitude has become clearer and crispier, and we can see 3 or 4 reflectors. Okay, and I was talking about multiple. See, this is multiple. Now here I have a multiple of first reflector at around 1.5, and I'm getting a multiple at around 3 milliseconds. Okay, same thing is happening here, which we will see in the coming slides. Okay, then someone was asking about gain or spherical divergence and everything. So this is a formula. This is the decay of amplitude with as we move away from the short point or thing. What do you call it? Away from the short point. Okay. So A is the absorption coefficient, means absorption of energy, and A naught is the actual amplitude. Sorry. Sorry. See, A is the amplitude at particular distance r, and A naught is the actual distance at offset 0. That means at the location of start point, and this is the distance at that particular amplitude corresponding to A. Okay, and this alpha is the absorption coefficient. By mistake, I have written A. Sorry for that. And R minus R naught. So see, obviously, if my start point is here, one start point is here, and one other geophone is here. Now energy is moving from here to here. So this distance is more than this distance. So if I want to find the amplitude at one particular distance, so that becomes A is equals to A naught at amplitude at particular distance. Then this distance corresponds to the amplitude with this, which we will find. And E is the exponential coefficient E, that is exponent A, E, and the alpha is the absorption coefficient, and R and R naught are the distances. So by this we can find the amplitude, and then we can apply gain according to that, so that according to this amplitude, to make and enhance this amplitude to make the decayed amplitude prominent. Okay. Deconvolution, types of deconvolution I have already discussed. Types of deconvolution, it's your duty to read. Okay, see, this was the muted data. Okay, and you can see here, this is the zoomed version. You can see here the reflectors. Okay, so what happened? See, you can see one more. See, this is the first reflector, and you can see here one amplitude is here. Okay, and then again there are two amplitudes here, and then this amplitude is not that clear. Okay, and this amplitude is also not that clear. Okay, so corresponding to different reflectors, the amplitude is decaying even after applying gain. So what we did, we applied deconvolution. We removed the effect of impulse response of the ground and the geophone, and suppress and compress the amplitude. So my amplitude corresponding to each reflector has become very crisp. You can see here this particular amplitude has been suppressed here. Okay, and amplitude corresponding to each reflector has become prominent, especially at the bottom. You can see here this reflector or amplitude, which is not that prominent in this scenario. Okay, and this is the velocity analysis. So see, my reflected data was like this, and then I picked the velocities. Okay, so you can see here I have picked the semblances, the maximum semblance. This is called semblance map, velocity semblance map. And you can see here the velocity is 1600 meter per second square, 1500 meter per second square, and so on, 16.87, 100, 1900, 700, like this. Okay, so I picked the here in this velocity analysis, we have to be very extra careful, and we pick the highest semblance corresponding to each reflector or each amplitude. So if this particular thing is incorrect, so I'll not get the straight or the amplitude at zero offset or in a one horizontal plane. Rather, I'll get either downward or upward curve. Okay. So velocity analysis is very important, and these velocity and after this velocity analysis, the velocity information which we will get, will apply that for we apply that to calculate the NMO velocity for bringing for NMO correction. See, this is the dipping reflector. Since now I have already done the velocity analysis, and I have found the two velocity for each reflector. So this hyperbolic amplitudes can be brought into one horizontal line, and then it is stacked to make a stack section, which looks like this. So this is the stack section of that particular area of KG basin. You can see the seabed is almost horizontal, and the angle is not that much. What do you call? Angle doesn't play a much bigger factor, because see, the area is almost of 100 kilometers. That is why, but here it's compressed. That is why it's looking like there is a dipping is happening, but it's gradually dipping. So there is no need of applying dip note here. And again, see here, the stack section is not that prominent. I could not find the reflectors here. That means I have to apply what? Migration. I applied migration. See, even there is a small dipping is happening. So I'll have to apply migration to bring the reflect. See, here the reflectors are not that prominent, and bow tie effect is happening everywhere. Okay. So now what I did, I applied migration, and then I now you can see the data looks much crispier. But after applying migration, we see some kind of noises on the top also, and in the data again. So what we do is, again we apply top mute here to remove all these diffractions. Okay, and we apply FK, frequency wave number deconvolution, to suppress the remaining noise to get a clearer picture. So I applied FK deconvolution on the migrated data, and now we can see how the stack section of the migrated, and after applying deconvolution and top mute, we see this the stack section is much clearer, correct? And now how to identify the gas ID. So in this stack section, we see higher reflectivity is happening here. That means this is the area of natural gas. Okay, and see, and this is my ocean bottom. Okay, or ocean surface. Okay, and you can and we see a similar kind of trend is followed here. That means this is my BSR, that is bottom simulating reflector, and there is one phenomena by which you can identify BSR. So what happens is, now suppose this is my ocean bed, or ocean bed, so it has some polarity. Okay, so my BSR will have bottom ocean bottom simulating reflector will have opposite polarity to the ocean bottom surface. Okay, now suppose if this is 0°, if it has a phase of 0°, so it will have a phase of 180°. It's totally opposite. So here you see, this is my polarity of this ocean bottom is black, but here we see that orange color, and it's mimicking. It's mimicking means it's copying the trend of the ocean bottom. Now this is my ocean bottom surface. Okay, and here you see it's mimicking. So that means this is the zone of gas hydrate, and it's trapping the natural gas, as which you can see here. This is the BSR. Okay, and this is the ocean bottom surface, and this is the high reflectivity zone. That means presence of natural gas. Thank you. If you have any question, please feel free to ask, or you can write it. Today's lecture was boring, and most of the students have left. Sorry for that. I wish most of the students would have benefited with this. Now the concept is clear. You guys can go ahead with the seismic data processing using seismic units, and if you have any doubt so as to what kind of filtering is should be applied to this particular data set, and what kind of deconvolution is applied. So there is one mantra is there, like you apply all the filtering, means different types of filter and different types of deconvolution, and you check for which parameter and for which filtering or deconvolution you are getting the best output. So that is why seismic data processing is a very time-taking process, and but it's very interesting as well. And especially when you work on software like Seismic Index, it becomes very interesting, because all the command and everything is in your hand. Means you have to give the command algorithm, you have to set the parameter. But in case of commercial software, you have to, in that also, you have to be very careful, but it's not that challenging, because everything can be done by just clicking the mouse, and you have to think of the parameter and everything. It means you will have to use your brain, but working on a software like Seismic Unix is much more interesting than going for a commercial software. With this, I'll end my talk, and thank you. And sorry if the talk was boring. And we started late, that is why it got so delayed. So if you have any question, you can shoot. You can unmute yourself and you can ask questions. Hello. Am I not audible or what? Thank you very much. So, hope it was fruitful and interesting. See, most of the theory part, which I already discussed as a concept, I skipped those, but I have kept it in a slide for you guys so that if you have any problem in understanding what I said, you can read those things and you can understand for yourself. So, and books are already I have referred, so you can. Any more questions? Please hurry up because it's getting late and I haven't had my dinner. It's going to be it's around 9:30. I have to take my medicines as well. So if you have any question, you can shoot, or then otherwise, then we'll meet tomorrow. Tomorrow I'll be discussing about another type of utilization of seismic data. I'll not go for interpretation because I'm not expert in that. I have done, but I'm not an expert in seismic data interpretation. See, interpretation you can do with the this process data also. Means you can see interpretation is nothing but storytelling. So you can make a story and you can publish and you can interpret the geology from process data also. But interpretation software used for interpretation enhances these features multifold times so that the features become much more prominent. And and I'm not an expert in those things. It's like just applying makeup to the process data. Now suppose a girl uses, or a boy nowadays use makeup to look better. So interpretation is that to make the process data look better and more presentable. So, and I'm not an expert in that. I know the things, I can explain those things, but I'm not an expert on that. So that is why I'm not going to discuss that. And tomorrow I'll be talking about velocity modeling, crustal modeling, velocity modeling. I'll be discussing about that. So please tune in. Tomorrow's class is going to be very, very interesting. Today we saw seismic data processing. Tomorrow we'll see velocity modeling and inversion of the seismic data. Okay, and how we can make. See, in this text section, we the layers and are not that prominent, but in case of velocity modeling, we can actually image the layers. And tomorrow we will discuss about that. With that, I'm going to stop sharing my screen and I'll take your leave. Good night. You guys have fun and enjoy. Stay healthy. Bye.